children, in this session we are going to see about bonding in metal carbonyls. So we know we discussed about different types of metals and ligand linkages, right? In this session we will see about the metal and the carbonyl linkage, especially about the homoleptic complexes here. You know what is mean by homoleptic complexes? It means a metal which contains the same type of ligand. So here it contains carbonyl. This type of carbonyls has a simple and definite structure. So few examples are given here for your reference. The first example is tetracarbonyl nickel 0. Okay, because here carbonyl is an neutral ligand. So if I am calculating for oxidation state for nickel, I am taking it as X. Plus how many carbonyl atom is there? 4 carbonyl atom molecule. So 4 into 0, since it is neutral ligand, on the whole it will be 0. So X is equal to 0. So in all the cases wherever the metal it is which contains a homoleptic ligand like carbonyl, in all the cases the oxidation state for metal is 0. Okay, so here in this first case 4 carbonyl molecule is there, so the shape of this compound is tetrahedral. And next FeCO5. So here the name of this compound is pentacarbonyl iron 0. Okay, and the shape of this molecule is trigonal bipyramidal. Okay, so these three will be on the same plane. These three carbonyl and the iron are present in the same plane. One carbonyl will be at the top and another will be at the bottom. So this shows trigonal bipyramidal shape. Next, hexacarbonyl chromium 0. Okay, so here this is an 6 coordination number is 6. We know what will be the shape of the compound if it contains coordination number 6. It is octahedral. Okay, so anyway, homoleptic carbonyl compounds will shows the simple and definite structure. Okay, and we see few more examples. That is so the first example is decacarbonyl dimanganese 0. Okay, here 2 manganese atom is there and total is 10 carbonyl is there. So we can use the prefix decacarbonyl dimanganese 0. Okay, so in this structure the two manganese are linked by manganese linkage. Okay, and the next example is octacarbonyl dicobalt 0. Okay, and here in this case 2 cobalt is linked by cobalt linkage, as well as these 2 cobalts are bridged by 2 carbonyl group. Okay, so here one carbonyl and here one carbonyl. So why we are speaking about this carbonyl means it is a very unique complex compounds, and they shows synergic effect in this compound. So what is mean by synergic effect, that we will see now. And here there is a bond between the metal and the carbon takes place. Okay, so this is very important. It is a bond between metal and carbon. Okay, so this metal and carbon may be sigma or pi, or this metal can and carbon will have 50% sigma character and 50% pi character. Okay, so see here children, in this picture I just drawn only one metal carbonyl bond here. So actually we know ligand metal, it is an electron deficient species, whereas the ligand is an electron rich species. So here the electron will donate a pair of electron to metal atom. So ligand has a pair of electron, it is donating its electron to metal, and this forms the sigma bond. Whereas there is another possibility is there, the metal it contains the filled uh, electrons in its orbital, right? That from that orbital it may donate electron to anti-bonding orbital of the ligand. Okay, so this is a pi bond. It is a metal which has a completely filled orbital, and electron from this filled orbital is donated to the pi star, that is an antibonding orbital of the ligand. So here this will forms the pi bond. So in the same case, in the same metal and carbon bond, we can see two types of bond. One will be sigma and another one will be pi. Okay, so this type of bonding is called synergic bonding. Okay, and this synergic bonding creates a synergic effect. Okay, so and or we can say this synergic bonding is an self-strengthening bonding. If the synergic bonding is more, then that complex will be more stable. Okay, so these are the things about the carbonyl, metal carbonyl compounds. Next, let's see about the stability of coordination compounds. So stability of coordination compounds is depend on the degree of association between the two species involved in that equilibrium state. See, let's consider here, I'm taken a metal and 4 ligands. I'm going to mix this in a solution form in aqueous state. So what happened, this metal and the ligand are bound together and they will form a complex, right? So metal ligand complex will be formed. So here an equilibrium is raised in between these two species and the complex, and this equilibrium is constant, is represented as K. Okay, so this is called as state of equilibrium or equilibrium constant or stability of formation. So larger the stability constant, the equilibrium constant is otherwise called as a stability constant. If larger the stability constant, then higher the proportion of the metal ligand that exists in the solution state. Okay, see, when metal and ligand are exist in solution state, even that metal is left free in very rare case. Okay, either it is linked by ligand or by it is surrounded by the solvent molecule. Okay, but the existence of a free ion is very rare in the solutions. So for simplicity, we are generally ignore this solvent molecules and we are just writing only the stability constants in a step by step manner. I am just going here I gave some equations. So let's see this equation in a detailed way, okay, in a step-by-step way. So first I am taken one metal and ligand. Here I didn't mention any solvent, okay. We are speaking only about the metal and the ligand. So one metal and the ligand, it forms an equilibrium with metal and ligand. So first it forms an first step complex like this, Ml. Okay, so here I am taken this equilibrium constant as K1, or otherwise I can say the first step stability constant is K1. So the stability constant is given as the concentration. According to law of mass action, we can write this equilibrium constant like concentration of the product by concentration of the reactant, right? So concentration of Ml divided by concentration of M into concentration of L. And this is step 1. In step 2, this Ml again linked with one more ligand and this forms Ml2. So here I am taken the constant as K2. K2 is equal to Ml2. Concentration of Ml2 divided by concentration of Ml into concentration of L. And in third step, the concentration of that Ml2 will bonded with one more ligand and this forms Ml3. Here I am taken as K3 as an equilibrium constant. So K3 is equal to concentration of Ml3 by Ml2 into concentration of the L, and this will go on. See, for example, for the complex Mln, I can write Mln minus 1 plus ligand will be equilibrium with Mln. Okay, so here the equilibrium constant I can write like Kn is equal to M concentration of MLN, this is a product by concentration of the reactant. Okay. So, in general, I can write the overall equation like M plus NL, that is N types of the ligand will forms MLN compound. So, they are in equilibrium. So, here I am taken the overall equilibrium constant as beta. Okay. Or we can say the overall stability constant beta is equal to concentration of MLN divided by concentration of M into concentration of L the whole power N. Okay, we are just raising this coefficient as a power in the formula. Okay, now here beta is the overall stability constant, and we calculated before no k1, k2, k3 and kn. So these are the stepwise stability constant. So directly we can relate this overall stability constant and stepwise stability constant like this. Okay, so we can write beta n is equal to k1 into k2 into k3 etc. into k1. So using this formula we can calculate the overall stability constant. So we can apply this stability constant in an example, in any example. So here we took the first example, that is tetraamine copper 2 ion. Okay, so here this reaction may takes place in step-by-step manner, but I here just written this everything in a single step. But in the first step we have only one ammonia, right? So CuNH3 2 plus, so this will be the product in the first step, and CuNH3 2 times on the whole 2 plus, this is the product of the second step, and in third step the ammonia will be in 3 times. Okay, like this we will get the product in step-by-step manner, but I just directly wrote that final step. So I can write beta 4, that is the overall stability constant for this complex, that is beta 4 is equal to, so the concentration of the product by concentration of the reactant. So what will be the reactant here? One is the copper and another one is 4 ammonia molecule, right? So concentration of the product by concentration of the reactant. Okay, so for in step by step we calculated that k value, that is a stability constant value. So for first step we got log k1 is equal to 4, and for second step we got log k2 is equal to 3.2. For third step and fourth step we got like this. So from this we can calculate the overall stability constant, or we can write this in another form, that is log of beta 4 is equal to 11.9. So that is nothing but the product of all these steps stability constant. So we can relate the instability constant with the stability constant. In general, we can say no, the energy of association and energy of dissociation. So energy of association will be the reverse of energy of dissociation, right? So like in the same way, here we calculated the stability constant for the formation, right? But that instability constant or dissociation constant will be reciprocal to the formation constant. So these are the things about stability constant in the coordination compounds. I hope you all understood this. Thank you, children.